that brings us back to summarize a fundamental property of all batteries. And that fundamental property is derived directly from the fact that the cell voltage is equal to the cell voltage under standard conditions minus RT over NF times the log of Q. And this, of course, is the Nernst equation. And the effect that this has on the cell voltage is profound because this quantity is very small, and this quantity is a natural log of a quantity representing the ratio of products to reactants. That means that the ratio of products to reactants has to be huge before the cell voltage changes. So let's look at the lead-acid battery. This is the battery that's in 95% of all automobiles worldwide. And if I look at the cell voltage of this lead-acid battery, I notice that there's a little tail at the top, and this is created by the fact that all reactants involved in this exist as reactants. And as soon as I have consumed a little bit of that, I enter a plateau that runs out 20, 40, 60, 80%, and finally it dives off the edge at just about 100% conversion of reactants to products. This voltage plateau is extremely important for all of the electronic devices you use. And of course, it's a problem when the battery voltage drops and the cell phone or the flashlight or whatever ceases to operate. But rather than saying that the cell is dead, it's better to say that RT over NF times log Q has now finally overcome the cell voltage under standard conditions. Let's look at another battery type, the alkaline battery. And this is very common in electronic systems. And the question is, the alkaline battery holds its voltage plateau because, one possibility, it has low internal resistance. That is, it allows electrons to flow out of it without any impediment. That turns out to be incorrect. It has high internal resistance. That turns out to be incorrect because the internal resistance has absolutely no effect on the voltage plateau. The third possibility is that RT over NF is small, in fact, very small, and that is correct, and it's true of virtually every type of battery. The fourth possibility is that log Q doesn't change appreciably because the activities refer to pure solids. We've already seen that that's completely incorrect because while pure solids are involved, so too are the cations in that electrochemical reaction. So which choice is correct? It turns out that number 3 is the correct answer, and it's a profoundly important aspect of all batteries. And when you're doing electronics design, it's very important because that stability in the voltage has huge implications for the design of electronic circuits.